Right now, as you read these words, sitting comfortably, completely motionless from your perspective, you're traveling at more than 2 million kilometers per hour through space. You don't feel it. There's no cosmic wind hitting your face, no sensation of speed. But it's happening. And here comes the question that keeps astrophysicists awake at night. Is that dizzying speed increasing, decreasing, or remaining constant? The answer could reveal the ultimate fate of our universe. Let's start with the basics, because before asking ourselves whether Earth is accelerating, we need to understand something fundamental. Earth doesn't move at a single speed. We're caught in multiple simultaneous motions, like a ballerina spinning on a carousel that's itself on a moving train. Each layer of movement drags us in a different direction, at different speeds, and each has its own story to tell. Earth's 4 velocities, a cosmic dance in layers. The first movement is the most intimate, Earth's rotation on its own axis. Depending on where you are on the planet, you're moving at different speeds. If you're at the equator, you're traveling at approximately 1,670 kilometers per hour. That's the speed needed to complete a full rotation of 40,075 kilometers in 24 hours. If you live closer to the poles, your speed is lower. At the poles themselves, you're technically just spinning in place. But here's what's interesting. This movement isn't constant. Earth is slowing down. Every century that passes, days lengthen by approximately 1.8 milliseconds. Sounds insignificant, right? But 400 million years ago, during the Devonian period, an Earth day lasted only 21.8 hours. The year had approximately 400 days. Fossil corals from that era preserve daily growth rings that scientists can count, confirming this gradual deceleration. The culprit? The Moon. The tidal forces that the Moon exerts on Earth's oceans act as a cosmic brake, stealing rotational energy from our planet. And while Earth slows down, the Moon moves away from us at a rate of 3.8 centimeters per year. This exchange of momentum between Earth and the Moon is a perfect example of conservation of angular momentum. The Moon isn't just moving away, its orbit is slowly expanding. In the distant past, about 4 billion years ago, the Moon was much closer, perhaps only 20,000 kilometers away. The tides it caused were monstrous, waves hundreds of meters high that swept across the primitive oceans every few hours. Days lasted barely 5 hours. The Moon appeared enormous in the sky, occupying a visual area 20 times larger than now. But rotation is just the beginning. While you spin with Earth, you're also orbiting around the Sun at 107,000 kilometers per hour, or nearly 30 kilometers per second. At that speed, you could travel from Madrid to New York in less than 3 minutes. Earth completes this elliptical orbit of 940 million kilometers in exactly 365.25 days. And here's the fascinating part. This orbital velocity is extraordinarily stable. We thought the orbit was perfectly constant, but precise laser measurements revealed something curious. The Sun is constantly losing mass. Every second, the Sun converts 4 million tons of matter into pure energy through nuclear fusion. That mass is gone, radiated into space as light and heat. And when you lose mass, you lose gravity. The consequence is that Earth is moving away from the Sun by approximately 1.5 centimeters per year. It's a minuscule amount on cosmic scales, but it means our orbital velocity is decreasing almost imperceptibly. In a billion years, Earth's orbit will be significantly wider, but don't worry about cooling. By then, the Sun will have heated up so much that our oceans will have evaporated anyway. Interestingly, there are other factors that affect our orbit in subtle ways. The other planets in the solar system exert small gravitational perturbations. Jupiter, with its colossal mass, occasionally tugs at Earth a little. Venus, at its closest approach, also contributes. These tugs are minuscule, but over millions of years, they cause Earth's orbit to oscillate slightly in its eccentricity, inclination, and precession. These cycles, known as Milankovitch cycles, have periods of tens of thousands of years and are responsible, in part, for the ice ages our planet has experienced. Now comes where things get truly dizzying, because while you orbit the Sun itself isn't stationary. Our entire solar system is revolving around the center of the Milky Way at about 828,000 kilometers per hour. Yes, nearly 1,000,000 kilometers per hour. At that speed, we complete one galactic orbit every 230 million years, what astronomers call a cosmic year. The last time Earth was in this position in the galaxy, dinosaurs didn't exist yet. We were in the Triassic, and the supercontinent Pangaea had just begun to break apart. During our galactic orbit, we pass through different regions of the Milky Way. Sometimes we go through the spiral arms, where stellar density is higher, and the risk of close encounters with other stars increases slightly. Other times, we navigate through calmer regions between the arms. We also oscillate vertically, crossing the galactic plane approximately every 30 million years. Some scientists have speculated that these crossings might correlate with mass extinction events on Earth, though the evidence is controversial. But even that isn't the end of our cosmic dance. The Milky Way itself is moving. Our galaxy is part of a group of galaxies called the Local Group, which includes Andromeda, Triangulum, and about 54 dwarf galaxies. And this entire group is moving at approximately 2,160,000 kilometers per hour, or 600 kilometers per second, toward a region of space that astronomers call the Great Attractor, a concentration of mass so immense that it gravitationally attracts thousands of galaxies within a radius of hundreds of millions of light-years. The Great Attractor itself turns out to be part of an even larger structure called the Laniakea Supercluster, a complex of more than 100,000 galaxies that extends across 520 million light-years. Our local group is barely a dot in this vast structure, and Laniakea, in turn, is being pulled toward another massive concentration of matter known as the Shapley Supercluster. It's like cosmic Russian dolls. Each level of structure we discover is contained within another larger level. So, when we add up all these movements, rotation, plus solar orbit, plus galactic movement, plus local group movement, we're traveling at more than 2 million kilometers per hour relative to the cosmic microwave background, the residual radiation from the Big Bang that permeates the entire universe. That's our absolute velocity, if such a thing exists in a universe where everything is in motion. The discovery that changed everything. The universe is accelerating, but here comes the twist nobody expected. For decades, astronomers assumed the universe's expansion was gradually decelerating. It seemed logical. The Big Bang had launched all matter outward, but the gravity of that same matter should be slowing the expansion, like a ball thrown into the air that eventually falls. The question wasn't whether the universe was decelerating, but how much, and whether it would someday collapse upon itself in a big crunch. In 1998, two teams of astronomers, one led by Saul Perlmutter and another by Brian Schmidt and Adam Rees, were studying Type 1 as supernovae in distant galaxies. Type 1 as supernovae are stellar explosions so consistent in their brightness that they function as standard candles. If you know how bright they are intrinsically, you can calculate their distance by measuring how dim they appear from Earth. And by comparing that distance with the speed at which they're moving away, you can determine the universe's expansion rate at different moments in its history. The results were impossible. The distant supernovae, which show us what the universe was like billions of years ago, were farther away than they should have been, much farther. Both teams obsessively verified their data. They looked for errors. They reviewed their calibrations. They repeated the observations. They consulted with colleagues looking for possible flaws in their methodology. But the evidence was incontrovertible. The universe isn't decelerating. It's accelerating. Imagine throwing a ball into the air, and instead of slowing down and falling, it begins to rise faster and faster. That's what's happening with the universe. 7 billion years ago, the expansion began to accelerate. And every second that passes, it accelerates a little more. Distant galaxies are moving away from us faster and faster. In 2011, Perlmutter, Schmidt, and Rees received the Nobel Prize in Physics for this discovery that transformed our understanding of the cosmos. The impact of this finding was seismic. The scientific community initially reacted with healthy skepticism. It was too strange a result, too unexpected. But as more observations accumulated from different telescopes using different techniques, all pointed to the same disturbing conclusion. In 2003, the WMAP satellite measured fluctuations in the cosmic microwave background with unprecedented precision, independently confirming the acceleration. In 2013, the Planck satellite provided even more precise measurements. There was no escape. The acceleration was real. But the discovery raised an even deeper question. What's driving this acceleration? Gravity can only attract, it can't push. There has to be something else, something that counteracts gravity, something that's separating the universe with increasing force. Scientists called it dark energy, not because it's dark in the literal sense, but because we have no idea what it really is. It's dark to our understanding. And here comes what's truly disturbing. According to our best measurements, dark energy constitutes approximately 68% of all the energy and matter in the universe. Dark matter, that mysterious substance we can't see, but whose gravity holds galaxies together, represents another 27%. And all normal matter, the atoms that form stars, planets, you and me, everything we've ever seen, is barely 5% of the universe. We live in a cosmos dominated by things we don't understand. The nature of dark energy remains one of the greatest mysteries in modern physics. The most accepted hypothesis is that it's an intrinsic property of space itself, what Einstein called the cosmological constant. According to this idea, empty space has energy, and when the universe expands and more space is created, more dark energy is created, which further accelerates the expansion in a feedback loop that never ends. Other theories propose that dark energy could be a dynamic quantum field, something that changes with time and space, similar to the Higgs field that gives mass to fundamental particles. Some scientists suggest we might be misinterpreting gravity at cosmic scales, and that we need a new theory to replace Einstein's general relativity. But so far, no alternative has been able to explain all observations as well as dark energy. The final destiny. Where is this acceleration taking us? The implications are astonishing, and frankly, a bit melancholic. If the accelerated expansion continues, the universe will head toward what cosmologists call the Big Freeze, or heat death. Over time, galaxies will move so far apart from each other that they'll disappear beyond the observable horizon. In trillions of years, an observer in the Milky Way if anyone is observing, will only see their own galaxy in an ocean of absolute darkness. Stars will go out one by one. The universe will become cold, dark, and empty. But before reaching that distant destiny, fascinating events will occur. In approximately 4 billion years, the Andromeda Galaxy will collide with the Milky Way. Despite the universe's accelerated expansion, Andromeda is close enough and gravitationally bound to us that local gravity overcomes the expansion. The two galaxies will merge into a giant elliptical galaxy that astronomers have already dubbed Milky Way. From Earth, if it still exists, the night sky will be a dazzling spectacle of star formation and gravitational chaos. There's an even more dramatic scenario, though less likely with current data: the Big Rip. If dark energy continues to strengthen, it will eventually overcome not only the gravity between galaxies, but also the gravity that holds galaxies together, then stars, then planets, and finally even atoms themselves. The universe would literally tear itself apart at a fundamental level. Some models predict this could occur in about 22 billion years. But this would only happen if dark energy is much stronger than we currently believe, if what physicists call the equation of state parameter of dark energy is less than -1. There's also a third, more speculative scenario: the Big Bounce. Some quantum gravity theories suggest the universe could experience cycles of expansion and contraction. In this model, when expansion reaches a certain limit, some unknown quantum mechanism could reverse the process, leading to a collapse followed by a new Big Bang. We would be part of an eternal, cyclical universe. But this idea, though intellectually attractive, lacks solid observational evidence. Now let's return to our original question. Is Earth accelerating? The answer, it turns out, is deliciously complex. Earth's rotation is gradually decelerating, losing approximately 1.8 milliseconds per century due to the Moon's tidal braking. Our orbit around the Sun is also imperceptibly decelerating as the Sun loses mass and we move away from it, though this change is so slow that our descendants in 1 million years would barely notice it. Our movement around the galaxy is probably quite stable on human timescales, though it varies slightly as we pass through different regions of stellar density, and the Milky Way's central bulge exerts different gravitational forces on us. But in the broadest sense, yes, we are accelerating. The universe itself drags us in its accelerated expansion. The space between our galaxy and distant galaxies is stretching faster and faster. We're surfing a wave of cosmic expansion driven by dark energy, that mysterious force that dominates the universe and whose nature we're only beginning to glimpse. What's truly extraordinary is that we live in a unique cosmic moment. We're technologically advanced enough to detect and measure this accelerated expansion. But we live at a time when distant galaxies are still visible. In the distant future, when expansion has pushed galaxies beyond our cosmic horizon, it will be impossible to observe evidence of this acceleration. Future astronomers, if they exist, might think they live in a static universe formed by a single galaxy. They would have no way of knowing that a vaster cosmos once existed. We are witnesses to a universe in transition, at a moment where we can still see the fingerprints of the Big Bang in the cosmic microwave background, where we can observe galaxies formed when the universe was just a fraction of its current age, where we can measure the acceleration that will determine the fate of everything that exists. It's an extraordinary cosmic privilege. So yes, you're traveling at more than 2 million kilometers per hour. And in a very real sense, that speed is increasing, driven by the most mysterious force in the universe. You can't feel it, but it's happening. Every second, the space between us and distant galaxies expands a little more. Every minute, we move a little faster toward a cosmic future we can barely imagine. What do you find more astonishing? That we're traveling at these dizzying speeds without feeling anything, or that the universe itself is accelerating toward an uncertain DC? Leave me your thoughts